Hello, how are you doing? Let me see. Hold on 1 second. So we have a couple minutes if we can download our lab. Okay. So check out Canvas. Your lab 2 is on Canvas. I will go through the procedure for lab 2 with you. In case you have questions, you can ask. Okay, let me turn on caption. Hello, everyone. I see you. How are you doing?
Hello.
Good. Hi. Well, today we're going to do LC-3 finally. So you are going to do assembly today. I'm good, thank you. A little cold and rainy. I'm on campus. So as we talked about before, if you haven't downloaded your LC-3 on Windows, you can go to modules and then you will go to your LC-3 resource page, which is this one right here. Okay, I think I also put a link on your lab. Now, for those of you who are using Mac OS, there are 2 links for the simulator down here. So if you're using Mac OS, you can use any editor. If you're using Visual Studio Code, Notepad++, Sublime, any editor that you have been using for programming, you can use that. The good thing about editor is it does count the lines, and if you don't have an editor, you can also use a text editor in your OS. Like in Windows, you have Notepad, but you have to save your file as ASM, and let's explain that. Now, for those of you who use Windows, once you click the site, you're going to download an executable. I'll demo it. And so once you get here, you're going to see version 3.01, and this is for Linux. So for those of you who are using PC, you would download this. Okay, and it's going to come down as an executable. Then you're going to open it, and it's going to ask you to extract. So you just click unzip. And what's going to happen is it's going to put it on your C drive. So you will find it on your C drive, and there's a folder called LC-3. You can place that folder, copy and paste it onto your desktop or another drive if you want, like a flash drive, that's fine. Inside it, so once you have it downloaded and unzip, you can go to like this PC, C drive, and find the LC-3 folder. But what I'm going to do is I'm going to find mine in my CIS11 folder. Okay, so it will look like this. And there are 2 components to the app. You are going to have edit for editor. That's where you're going to write your code. And you're going to see that like this. Okay, so when you open it, it's blank. And then once you assemble the program, and I'll walk you through the process, you are going to simulate. Okay, that's when you're going to run the program. Now, for those of you who are using Mac OS, let's say that you're using this website. You have to write your code in a text editor, like I said, and you're going to have to save it as a .asm file. You can use the website to assemble your program and run your program. So this is going to be your simulator for the assembler is here and the run is here. And to upload your code, you would click this. Okay, and you just simply add your file in here. Okay, so once you upload your file, you're going to assemble and you're going to run. So it has to be assembled. But let's start first on what we're going to be doing today. So today we're going to work with input output in text. So basically we're going to do a hello world program. But before we do that, I want to explain to you how your instructions work, how your opcodes are. So when you're working with assembly, most assembly language uses a word size for 16-bit. Basically, it's a storage location. It is addressable, and it uses that to retrieve the instruction. Remember that we're working with RISC, reduced instruction set. So that means that we are going to work directly with registers. So these are, just think of them as temporary files to be able to store instructions and values. There are a total of your 8 general registers. It's going to be register 0 through register 7. Some registers are specific to a certain purpose, and some you can just use it as temporary storage, like when we move data across from one area to another in our processor. So everything that you want to bring into the microprocessor has to go to a register, right? So it needs to temporarily store there before it can execute or operate. Okay. And so it talks about the register file, and that way we can use it for instructions, we can use it for label, we can use it for values, like when we're adding values, etc. Now for our opcodes, those are the things that we're going to tell the computer to compute. That means that we can use the opcode to add, we can use the opcode to load, like when we're bringing in some form of label or data. And that will take up only 4 bits. So out of the 16 bits, the beginning 4 bits of your opcode is going to be for the beginning of the 16 bits, your word is going to be for opcode. The rest, it's going to be used for different things, from addresses to values. Okay. So we have to find a way for the user to be able to interact with the system. And on the assembly level, we have to do some conversion. Okay. So here what I did was I put down some general information on the higher level IO support, especially when you have data that is coming in from the keyboard. What you're going to have to do is you're going to have to take those characters and convert them to values, to numbers that the computer can understand. So some of the things that we want to identify for opcode, you always start your program with an origination address. And for LC-3 and most assembly language, that is at hex 3000. That's where your program is going to load. Okay. And remember that your input is going to be text and your output is going to be text, which is going to be in ASCII characters. Okay. So keep that in mind. We always start our program with .org, which is the origination, and it tells the computer that that's where our program begins, the start address of the program. We always end our program with .n, and that's the end of your program. So if you don't have a .n, when you assemble, it's going to throw an error. When you see a .blkw, that's called a block word. And what that does is it allocate a certain size. Remember that each word is 16-bit. So if I have block word n, the n is going to be the value that the computer is going to refer to for the number of block words that it's going to allocate in the memory. We can also do a fill, and you can fill it with a hex value, which is represent with the small x. You can fill certain things as a label. So filling, think of it as like initializing or declaring in C or C++. So we can fill it with a certain value, and usually we use hex value to represent an address or numerical value. Okay. So what that does is it's going to allocate one word, which is 16-bit, and it's going to initialize whatever the value that you give it for at that 16-bit. And I will show this in the programming side. Whenever that you're working with string, you are going to do a .string z. So strings, and this is what it's going to do is going to cut up the space enough to fit your characters for your string. So as you are familiar with, some of you already took, right, programming like C++, you know that string is null terminated, so it needs that one extra bit for null terminator. Okay. So the way that we write our code is like this. Your label, you don't always have to have a label. Think of a label is like an identifier. We give it a name. Then your opcode, what it's going to be doing, that's required. The operands, that could be value or addresses. And anytime that you want to comment, you use a semicolon in LC-3. Okay. So we learned that there are registers 0 to 7, and that's specifically used to bring in data or instruction. So you have to bring everything in through a register. Your numbers, when you're working with numbers, if you're using decimal, it's a hashtag. And when it's a hex value, it's going to be a small x. Or it could be a capital X. It's not case sensitive. Your labels, that's always going to be at the beginning of the line on the left side, and that is simply a symbolic name. If you're familiar with C, C++, they do use label. A lot of the modern way to program, we don't normally use label, but labels are very important in assembly because you can send the program, your code can be 1,000 line, but you can jump from one area to another area of your code by using label. Okay, any question? Okay, now let's talk about pseudo instructions. Pseudo instructions is a way to use trap instructions. So these are code that allows you to have specific action. Okay. So if I have something like hi or hello, right? In C++, we would have my string as a variable, and then we would declare our text as a group of characters and that can be represented as string. So the system would then need to convert that character from an ASCII value to a number. And today we're going to take a look at our ASCII table. And so to store, it stored that value as binary after it converts it. But if it's inputted as an ASCII, converts it to a numerical value, when we output, we have to take that numerical value and convert it back into ASCII so it can output text. Okay. Now to work with text, we're gonna, or our program in general, we're gonna have pseudo instruction. Halt is to halt an execution. So for example, if you have a function, right, and you want that function to be executed, but at one point you want to stop that function, you are going to issue a halt. And what that does is when you simulate, you're going to see that it's going to trap at hex 25. This is a specific instructions that is used on the simulator to show you that this is where the program going to stop. Okay. And it's going to print a message on your console that the program has been halted. Okay. Then we have an in. This is a way for us to read one character on the keyboard. And it's going to revert to register 0. So register 0 is specifically for in. Okay, so when you say in, the system is going to try to obtain the value that you give in register 0. So it's going to wait for the input. So when we say in, it's going to wait for the user to strike a value on the keyboard, and whatever that value is, it's going to load it to register 0. It's going to store it there. And we can take that value and we can do something with it, right? So when you say in, right, the system is going to try to find the value that whatever the type in value is from register 0. When we output, we can use a pseudo instruction out. Right, in is trap hex 23, out is trap hex 21. And out is going to write one character from register 0 to the console. Okay, so in is from the keyboard to register 0, out is from register 0 to your console, which is then being displayed on your monitor. Get C is a way that we can read also one character from the keyboard, one character, right, at a time. And that character is also stored on the register 0. So there are two ways that we can have an input, through in or through get C, and you will see the difference. We can also have another way to output, which is puts. And puts, instead of only outputting one character, puts give you the string. So it's going to display the entire string that's initialized, and it's going to use the address string in register 0. So register 0 is going to have the address of what where that string is. Okay? Any question? All right. So I'm going to demonstrate using the Windows version of this. Like I said before, and if you didn't catch it, you can use any text editor to write your program. Or if you're using Windows, you can use edit in the actual application, the similar application to write your program, which is what I'm going to be using. But if you have text editor from your IDE that you want to use, as long as you save it as an ASM file, you can assemble it. Just make sure that you can find the file later on. Okay. So when I do this in class, I normally have a student create a folder. And so it's always good to have your program in a folder. So that way you can go and find, because when you assemble your program, okay, let me go to unit 2 so you can see. After you assemble your program, this is my original program. It's going to create more additional files, a binary file and a hex file. Okay. So it's always good to have a folder where you will be able to store your file and find it. So when you assemble your file, you're going to have additional files with it, and it's going to use one to be able to create. So you also have symbol file and so on. Okay. So the ASM is what you write for the code. So once you have your editor, okay, you're going to open up a new file, and this is my editor. And you would write your program. I screenshot it for you here. So in this program, at the beginning, the first line, these, as you can see, that they're leaded by a semicolon. So those are comments. Okay. Comments are ignored by the simulator, just like how comments is in C++ or Python or Java, right? It is just a way for us to denote certain section of our code. Now, at the university level, they are going to expect you to put down information about your program. So I wanted to put that here so you can see your course, your name, your lab, right? And then your program information, what is going to be your input, what is expected as an output, are there any side effects? Okay, so we put none, there's no side effects, and how to run the program. Now, this is a good practice. Must you put all the comments? No, right? So for my class, let's get into a habit of adding the comments about your program. So later on, you can refer to it in case you need to look at it again. Okay. So all of these lines are going to be your comments. Okay. The next part right here, you notice that there's a .orig. That's origination. We always start our program in this class, right, in assembly, with an origination address. By practice, we started at hex 3000 because when you look at the simulator, that's where your program is going to load. Okay, so always start with the origination address. Now on the next one, the next line is LEA-R0HW. So I am gonna indirectly load, and we'll talk about different loads in the next week. LEA is a way that we're going to take the address of our string and load it to the register 0. This register is going to be used to be able to output. Okay, because I'm simply doing a hello world program. I need to store it into the register so that way I can take the value and be able to display it onto the console. So here what I'm doing is I'm going to load the address, right, which I call HW of our strings. Okay. So in order to work with the string, you are always going to load it to the register 0. And here I'm using HW. Think of it like an identifier. And with that, I would then later declare my string. So I load the address of the string. Then I have a pseudo instruction called puts. And it's going to take my string and output it onto the console when it gets to this line. And then after that, I want it to stop. So it's going to halt. So I have a halt here. Because we're saying that we're loading HW to register 0, now we're going to declare what that HW is. So think of it like a variable where we would initialize our string. So HW, and we would say dot string, so it's going to store strings. And then we're going to put in hello world. This is my first LC3 program. Make sure that we enclose our string with quotation marks. And at the end of our program, we're going to do a .n. Okay. So when you put these in, it's going to look like this. Okay, I know that the thing is small. I'll try to expand it for you, but there's not a lot of ways to really increase the text size. So that's why I screenshot it for you. So once you have your program written, not many lines, right? We have 1, 2, 3, 4, 5, 6 lines. And later on, you're going to see your program is going to be getting longer and longer. So we'll start with the simplest one. Now, if you're using your text editor, you just simply do the same thing. You can go File, Save As. You would give it a name, hello world.asm. So I can type in hello world. And then you would say .asm. And that's really important. That would differentiate it with just a regular text file because it is an assembly file. Okay. Any question?
I have a question.
Yeah.
So the line that starts with LEA, we're creating a variable HW and putting it in a register called R0.
Right.
Okay.
And R0 is specifically for input and output. You have to use register 0. And so register 0 doesn't really store that HW, it actually stored the address of HW in this case. Yeah, but
So
you're right.
it points to the address then?
That's correct. When you do an indirect load, it actually is pointing to the offset or the memory location where that value is initialized. I have a chat question. Okay. So once you wrote your program, okay, before for the people who are using Mac OS, right? The link, you can find it on my LC-3 resources right here. You can pick either one. They're exactly the same, right? I'm using the LC-3 tutor one. So there's a small arrow up button right here next to assemble. You're going to click it. And this pops up and you're going to drop your files here. Okay. So once you add your files, you're going to assemble. Click this. Let me try the other link. I think it's pretty much the same. Yeah, there's an upload. Okay. You're going to upload your file, put it, and then I'm not going to do that, but click assemble and then run. For the Windows people, right, once you save your ASM, okay, there is a button on here called ASM. That's for assemble. Okay. Or you can go and you can click translate and there's assemble. There are two ways, translate, assemble, or you can click the ASM here. So I'm going to click the ASM. Now, if you have errors, if you type it wrong, it's gonna show you the error. Unfortunately, on the editor, on the program, the simulator program itself doesn't have the line. So that's why I tell you it might be better to use your text editor and save it and then open up your editor to assemble. You have to assemble it. Okay. So it tells me that it passed twice, no zero errors here. So now I'm ready to simulate. So I have to click ASM. And for those of you who are using online, upload it and then assemble. Okay. Any question? So once I assemble, then I can run my program. If you're using the website, right, you run your program. Now, to run my program in Windows, I go back to my LC3 folder. I have a thing called simulate. It looks like this. Oops. Okay. And so my simulator is like this. See how it starts at 3000? Okay. But right now, I don't have any program in here. What I need is I need to take the assemble program and open it here. So you can click the open load program here. And then you go and find your program. So I have the hello world program, right? Okay. So once it's loaded, you're going to start seeing your symbols. Okay. So see how you tell it to originate at 3000? It's going to show there. And then every single line after, right? Now, do not rely on what's on top here because remember that this is temporary. So it will move through And so basically after I assemble, I load up my program and then I click the green arrow or run under execute. You can also press F5. Okay. So after I load my program by opening it up in the simulator or simulate, I'm going to click run. And so you notice that there's another window that pop up, right? It shows my string. Hello world, this is my first LC3 program. So if you assemble successfully, then you open up your simulator, open up your assemble program and run it. And you can also step through it. We're going to talk about jump 2 next week. You should have an output. And this is how you output text on LC3. You're going to find that C++, higher level programming language, even with Java, right? System print line is a lot simpler than what you would see with LC3. It takes a few steps. So what you're seeing here is at the low level, you have to create a section of memory where you would label it, load the string to it, take that address and put it to the register so that way the microprocessor, the processor can see it and then to be able to output it. Okay, this is how you work with string. Any question? So what we learned from this is we originate at 3000 always. We use register 0 for input and output. We want to use indirect load, LEA, and I'll talk about different load next time. And pseudo instruction to be able to output a simple program with string. And then a .n at the end of your program. All right. Any questions?
For the HW line of code,
Mhm.
does it have to be specifically HW or does it? Or
No.
it can be-
So the symbol that you use here, the identifier symbol, that could be anything you want, but you don't want complex because in an LC3 program, it's meaningful, right? HW stands for hello world. You can also put hello, but I wanted to keep it minimal as possible because you're going to find that if you give yourself a very long label, it's going to be harder to read. So you want your code to have readability, right? But it should be meaningful. Okay, just like how you declare your variable in C++, you want it to be like your code has to have readability, but it also needs to make sense what that identifier is, what that container is. Yeah, it doesn't have to be exactly the HW, but I want to show you that you should use something simple. Good question. Other questions?
Yeah. For the screenshot, do you want us to post that in the Word document as well? The lab
Yeah.
Word document. Okay.
Yeah, just one document. There are times that you have to answer questions. You can type out your answer there and upload one time. That will be better for me. You don't have to upload individual screenshots. Some students do that. It's fine, but I just want to save you the time. So put it on one document and just upload one time. Okay. So in the past, I actually do this in week 3. In week 2, I do gates a little bit more, like you have to draw gates. But I omitted that because I felt like, that can impose some challenges as it doesn't really tie back into what we do, which is assembly programming. So I think for the lecture part, we address the gates and then, we would do more programming for the rest. string directive to have exactly one operand, but found 8. Okay. So strings directive with one operand, what found 8. Perhaps you need to check your typing. Are you enclosing your string in quotation marks? And then for your strings here, it needs to be dot strings, not just strings with a Z. Save it for now. Let's address it. If I'm not able to help you fix it, we can work on it after the session. You can stay on Zoom and then I'll have you screen share and we'll take a look. Okay. Syntax is very important. Okay. That's fine. Yeah, so check how you type, because if you don't have it correctly typed as an instruction, it's gonna, yeah, dot strings need to be how it's supposed to be. Okay, so if you type it wrong, correct it and then reassemble it every time that you correct your code. Okay, so some of the things that I want to talk about before we proceed. Now, Simulator is a software. It's gonna be the best as it could be. Sometimes there's hiccups, okay? So don't be surprised, right? So what you can do is if you fix your program and assemble it, and for some reason it's still showing you the same output, possibly it could be another error, but what you can do is you can reinitialize your machine. So this is for the simulator on Windows only, right? You can go File, right? Reinitialize the machine. So what this does is it clears out everything. It's kind of like reset. Okay. So from one program to another, this is my recommendation. You should always, right, reinitialize your machine before you load the next program. Because sometimes there are remnants of data that remains in a certain area or a certain address. And what will happen is if it does stay there and it doesn't clear out, it's going to change your output or have an error in your next program. So from one program to the next, we want to go to File, reinitialize the machine. Okay. So once you finish running your program and you have it output on your console, right, you just simply take a screenshot. Okay, I want your code, I want your simulator, and I want your output. You can put it all on one area, you know, minimize it. 3 small screen, that's fine. Okay. So as you assemble, you're going to see a few things. Okay. When you load your program to the simulator, right? You notice that there is an object file. So once it's assembled, it's going to create a few files. It's going to create a symbol file, a hex file, a bin or a binary file, and an object file. That object file, like I state in number 10, is what you are going to use to simulate. Okay. OBJ. And then when we run, so we spent a lot of time on the hexadecimal last week, right? As you can see, the simulator, what it tells you is at the end of the program, when it finished giving you all the things that you ask it to do, right? it's going to end up with specific values at a certain register and at a certain location. This jump to option allows you to move up and down your simulator. So for example, at the end of my program, I'm at this address, right? But let's see, I want to come back to the beginning and see if things are still there. So I can do a hex 3000, right? So my program started here, but when it finished calculating, it was at a different region of the memory to give me the output, you see? And your register 0, there are sometimes you are going to see like things are clearing out or not being used, and then sometimes there are values or addresses that's specific to it. But like I said before, don't always rely on register. If you do step by step, it should show you all the steps on what the register is storing at that moment in time. But at the end, what you're going to have is register 1 usually is always going to have a -1, where that's going to give back. So it's going to, you know, like how you would have the return 0 at the end of your C++ program. What that does is it gives back all the resources. So that way it will free up the location for additional steps that it needs to use for like other processes and other instructions. Okay. All right. So on the next one, we're going to use the example, the first one, and we're going to create one with 2 strings. Okay. It's a little harder. So on the second program, we're going to say this is my second program in LC3. I'm learning assembly program. Okay. And I have it written. Okay, hope you can see. All right, so on this program, I have comments like before. I said this is my second exercise in lab 2, my second program. The description for this is LC3 program that display. This is my second LC3 program. I'm learning assembly language and I want to output that onto console. Input, nothing. Output, right? Those 2 strings. Side effects, no. And then to run, simply assemble the program, open simulator, load the program as object file, and then run the code. Just like the last program, I have origination address, hex 3000. And just like the last program, I'm going to have LEA R0 HW. I'm still using the same label. That's fine. You can use different label. That's up to you. Remember that register 0 can only be used one at a time. So what I have to do is I have to load it with an identifier, output it, then reload it again with another identifier, output it, and then end the program. Okay, so it is a sequential step because I want to show the first string first. So I have to load it first, puts it, then load the second string address, puts it, stop. Okay, so here, this is why I have LEA R0 HW. Then I do a puts, right? Because it needs to take what's in register 0, as that is a temporary file, output it. Once it outputs it, then I can load the next string to the register 0 using a different identifier. So I would do an LEA R0 HW2 puts and then halt. And I comment, you don't have to comment every line, but I kept the comment so that way you can see and understand. Then what I declare, I would do hw.strings. This is my second LC3 program, and I use the line carriage here, just like C++ or Python or other language. You can use a /n. That's just for a new line carriage. And then I declare HW2 as a second strings, and I put I am learning assembly program. And don't forget the .n. So what that does is we load the string to the register 0 output, load the register 0 output, finish, right? Stop, and then finish up our program with a .n. Just like before, we can use any editor, any text editor, or if you're using the simulator program, you can use edit and type. Now, if you use your text editor, you have to use the assembler in this application, right? So once I have it, save it, file, save as. And I had saved it before as lab2 ex2.asm. Make sure that we put in .asm. And then we click save. So then we would use ASM button or assemble button. So you need to assemble it. Or you can click translate assemble, same thing. Now it has other buttons like B and X, that's to convert this file to binary and hexadecimal. But when you assemble, it does it for you. It converts those files for you. So once we assemble, we would have the OBJ or the object file, and that's the file that we need to use to simulate. Okay, so once I have that, I go to my simulator. I will go ahead and clear it. File, reinitialize the machine. I can then load the program. So open up the program. Exercise 2. Click open. It shows the start of my program at hex 3000. All the instruction I gave it. And then I simply click run here, or execute, run, or press F5. And then for those of you who are using the online one, right, check your code, make sure that you don't have any syntax error. Save it as a .asm and then upload it onto the online simulator and run it. So once we ran it, we would have the output like this, right? I have 2 strings. This is my second program. I'm learning assembly programming. So for assembly, that you can see that it's going to be step by step, okay? Higher level programming language, the compiler already took care of a lot of this for us. So when you say C out, right, this string, right, or C out my string, it's already loading that for you. But at the low level, you see that's using register or memory to be able to pull where you store your string or your variable and be able to load that so that way your monitor can display it. Right? You can see it on console. Any question?
Yeah, so for this program right here, you're only using one register.
Yeah, register 0 is specifically in LC3, it's specifically for input and output. No other register.
And then
Even
this,
if
I'm
I'm
sorry.
sorry, even if you use register 1 for your string, you still have to bring it to register 0.
And so there's 7 registers, correct?
That's correct.
And
8,
then
8,
8.
0 to 7.
And then another question on the side there, I see it has like NOP. What does that mean right there?
Yeah, so NOP doesn't have any kind of values, right? It's not being used. So those are just empty. When you have specific instructions and values, so this is for Word that doesn't have anything in it. So think about your computer RAM, right? You have a lot of storage, but some application, most application would not use 16 gig of RAM. Or if you have a lot of cache in your processor, it would not use everything. So simply these are just available location. These are addresses, right? That was not being utilized. But if we jump to this is at the end of the program, that's where it is, right? When you do the return value, you see how there's return. We'll talk about the ST and some of these. So not just simply indicated that there's nothing in it, okay? And then if I jump to a hex value, like the beginning of my program, right? It's still there. That's where your code actually load. But as it execute, you would see that it's further down because what happens is it's using other parts of the memory to be able to give you this output.
And so this simulator shows you all the addresses that are being used.
Some addresses that are being used, but all the addresses in the system. Yes.
Okay.
Yeah. So see how this, because our program is not long, you only use like 1, 2, 3, 4, 5 words, 6 words, right? For our code. And as you move down, you're going to see that there's another section that's being used. Later on, we're going to talk about the stacks and how we would intentionally create a section of memory for stack, and it's further down, right? So in a regular compiler, what you would see is for C, C++, right? Or even Java compiler using JVM, you're going to see that it has a reserved section of memory that it's using that to be able to bring in the declared variable, the declared array, your data structure, all of the components, the container. It's going to take that and it's going to put it somewhere so that way it can use it to operate. And that's the intention of the simulator, is to show you that even though your program is loaded here, this is where it initially store, right? Down the line, when you finish running the program, it's at a different section of the memory. And we're going to talk about how, the ACU handle that, right? The arithmetic unit is really looking at, what's coming in and then what part of the memory that it's going to pull from.
So I have a question regarding the order. Does the initialization of HW and HW2, doesn't matter, or do you just put it at the end?
It doesn't matter, but by practice you don't so LC3 and assembly in general, you declare data at the bottom. Okay. The reason for that is that you want the instruction and the label, and then you can modify the value. It's just the practice. And in general, I see the purpose for it, because a lot of the time the instruction is handled and you're using label, or you're using like some kind of symbol, and then you would tie that symbol to a certain value, and a lot of the times those values tie to an address. So by practice, we would normally declare things at the end. It's the opposite from your higher language, where we would declare, like, we globalize thing at the beginning. But in assembly in general, if you look at like other languages like ARM, the source code, a lot of the times they declare things at the bottom. Okay. So does it have to be necessarily in order? No, but in order, the reason why I kept it in order is so sequentially I know like the order that it's used. And we don't recycle, unlike the other languages, like you can reuse the label. No, the label is used for its purpose. So you can't reassign the value like how you do in C, C++, other languages. Other questions? Good questions. All right, let's do the next one. Okay, so take a screen capture for your output so I can see that you successfully did that. Okay. All right, so let's talk about add instructions. So one of the instructions, we can use it to add values, right? I think the term integers is kind of misleading in this class, because our integers in the human world really indicate decimal values. So let's say that we want to add integers. We want to add decimal numbers, right? We need to bring those values into registers. Okay, anything that you want to operate, you need to take them and load it to a register or add it to a register. Okay. So add is a way that we can initialize values. So let's say that I have variable 1 is 3, variable 2 is 4, and I want to take 3 plus 4. I should get a 7, right? So in this case, what you're going to do is you're going to take the 3 in decimal. You can tell it's a decimal by the hashtag, and add it to register 1, right? But the way that we use this is, if you look, the example that you see here, I'm going to pull it up bigger so you can see. It tells you to add register 3, register 1, register 2. Okay. So let's say that register 1 has 3, register 2 has 4. So if I take 3 plus 4, my output is 7. It's going to put it onto register 3. So the destination, the result is going to be the first register after the add instruction, right? The other registers are the registers that are being added, register 1 and register 2. Now here they're showing you, what if I have a value here, X, let's say, or register 1 could be any value, and I want to take that value and add it to 4. So value add 4, and it's going to have the result in register 3. Okay, so the first register after the add instruction is always going to be for the outcome, the result. Okay, and then the other registers or the values here are being added. Okay, I can also do a negative, or I can even use the complement. So I would do, not and then an add 1. So on LC-3, it allows you to use negative value. Other assembly language, you have to do the 2's complement. So when you subtract or divide, you have to do the 2 complement, which we will be doing so you can see. But in this language, you are able to use negative sign. So you can use that for subtraction purposes. So it shows you the example here. Okay. So what if I want to take the value adding itself? Or so let's say I have 5 in register 1. I want to take 5 plus 5. So 5, and then I add itself and put it back into register 1. So it's going to take 5 plus 5 equal to 10, update register 1 as a 10. Okay. Any question? So for the ALU here, we can use instructions, and you can, remember that your simulator treats everything with binary and hex. Mostly we would use hex value to initialize. Okay. All right. So on the next program, what it's going to do in this program, it's going to print a hex number. Okay. So we are going to output hex number. And we want to be able to use the value that we initialize. Remember that human sees ASCII. Okay, computer doesn't. It sees hex and binary. Okay, so in this program, I have the comments at the top. This is the third exercise. And it's going to output hex value, then run from the run instruction for my simulator. I would start the program with the origination address always at hex 3000. So you would do .org hex 3000. And in this class, the way that we clear register, so it's always good to clear register because you don't know what's still in it, right? Let's say that you have a very long program and you reusing the 8 register, let's say register 0 continuously being used. What if it's already have something in there, like a value, a number? So it's good to clear, and it's similar to how you initialize the variable at 0. Right? It doesn't have anything yet, and then you can reassign it with a different value by adding it. So here, when you do an AND, this AND allows you to clear the register. So I'm clearing register 0 with the 0. So basically, I initialize it at 0. So you would do an AND R0. Remember, this is the output. This is store the result, right? Register 0, right? And then register 0 with 0. So anytime that you AND something with a 0, everything becomes 0, right? We talked about that this week and last week. So when you AND any value with a 0, you're going to get 0. That's what we intend to do here. So you're going to AND register 0 with 0 and put it back into register 0. Okay. So this is the destination register, right? This is the register that you're operating and the value you're operating. So I take register 0, I AND it with 0, and put it back into register 0. So that means that we initialize or clear register 0. Then I'm going to use simple or label. And in this case, I'm going to use num. So I'm going to load the label num to register 0. Okay. So what that does is going to take the address of num and it's going to tie it to 0. This is a direct load, so we can also load value this way too. Okay. LD is a little different than LEA, and we'll talk about how and why, right? How it loads the value without going through certain things. So indirect load and direct load is a little different. So LEA earlier is load effective address, and load effective address does take the address and put it to the register. What we can do is we can load the value of the label to the register by doing a direct load. Okay, so we're going to load the label num to register 0, which has 0 right now. Then we're going to use another label called ASCII, ASCII, and we're going to load it to register 2. So these two labels, think of it like you declaring a variable right now. Declare variable num and declare variable ASCII. And then what we're going to do is we are going to take those and we're going to add them together. Okay. So num plus ASCII. right? Because num is at register 0 and ASCII is at register 2. We're gonna add them together and then put the result in register 0. And then we're gonna output. And then we stop. So, and I didn't do a dot N on this one, so don't forget, I cut it off when I did the screenshot, but let me show you. Okay. All right. So where we left off was we halt, right? The data, right? As Kevin asked earlier, your data declaration is here. So you have to say, oh, well, what's num then? What's in num and what's in ASCII? You didn't give it a number. This is where we can fill. There are several ways that we can introduce data or values to, the program. This is one way. A way is we fill it with a hex value. And in this one, I want to initialize num as hex 2. As you recall, hex 2 is 2 in decimal, right? Hex 2. So num right now is filled with hex 2. So when I load it to register 0, right, it's going to take the 2 and put it into register 0. And then ASCII, I fill it with hex 30. Remember, the hex 30 is not our decimal 30. Okay, it's hexadecimal 30. So once I load that to register 2 then would have 30, hex 30. When I add those together, right, that will be hex 32. So hex 32 is here at this time. Then I output, and then I would end. So you asked me, why am I doing hex 30 and 32? Okay, this is the reason why. Give me 1 second. If you find your ASCII table, okay, so here's an ASCII table. All right, if you look, I need to find hex 32. Okay. So between 30, if I look at the hex value 30, right, that's what we fill. What's the character? 0, right? If I look at 32 in hex, what's the character? 2, right? So what's the gap between this and the character? If I have a hex 32 and the character is 2, isn't that a 30 gap? Right? So the difference that you have to see is what we see as character, what is the hex value? So if I have 30 here in hexadecimal, then my character is 0. 31 is 1. 32 is 2. 33 is 3. So what we see as number, what is the equivalent in hex? And you have to see what the computer see as hexadecimal value when you introduce a text character. Okay? And that's important to note because it's going to make more sense when we go along with the next one. Okay. So once, and don't forget the dot N for this one, right? We talked about that at the end. Okay. When you're finished, you do file, save as. And then you would save it as L2EX3.asm. Save, assemble. So click the ASM. If you're using online, upload it and assemble. And then go to your editor. For those of you using PC, reinitialize your computer. Open up your file. Click open. Look at where your program starts. Right? Okay. When you look at this program, there's no output, right? I didn't tell it to put it to console, so don't look at the console. Okay? Because what you're going to see is you are not going to be able, we didn't convert it back to text, right? We simply say that, oh, this is the label, and I fill those. So that will be 32, hex 32. Okay, so see how when you fill, when you look your simulator, how you initialize 30, it's right there, right? This is the address, this is the fill. When you fill the num, it's right there. Okay, if you want to stay on in a little bit after we finish 4, we can talk about how you can resolve the issue on the Mac. And so if you have the fill, it's right here, right? And when you add it together, it's supposed to be in register 0, that will be 32. So let's run. Okay, we can jump it back. Okay. So as you see, this is where the end of your program is, right? Your num, your ASCII. And so when we add those num values plus ASCII value, you would have 32, hex 32. Any question? Now, when you're using the online simulator, right, your console is here. So you should see the output if all your after you assemble and run your program. So upload your file right here. Just drag it in, then assemble, then run. For the last 2 program, your output is here. For your jump to, just type in the address and it should go. Should be the same. Yep, your program should print too. Who knows why?
Well, you just explained it, right? Because you added the hexadecimals, right? And then when you look
Yes.
at the table, it's going to show too.
That's correct. It converted it for us, right? So you look at the offset, right? Very good. Thank you for following me, because sometimes that's hard for people to understand. When you have hex 32 right here, your text is 2. Yeah. So your program two, because it's 32, right? If you have 32 hex. All right, so we're doing good. Okay, let's move on. Okay, on the next one, this one has a little bit of input and output offset. Okay. So it's like you asking the user enter a number, right? You take that number and you compute and then output. So in this program, we are going to start it as hex 3000. You're going to have an input. You are going to load a label hex N30 for subtracting 30 to register 3. We're going to use this label hex N30 and load it to register 3. We're going to take that and we're going to add it to register 0. Okay. The reason why we add it to register 0, remember that you have an in. Okay, so Ashley said that if you're using the LC3tutor.org, it works, but the other simulator does not, in case anyone has the issue. Okay, thank you. I'm not aware that the other one doesn't, but because last time I taught this, they were using both. So, but thank you very much for saying that. So the LC3 tutor, that one works. All right, so we load the label to register 3. We take the input, which comes from register 0, and we're gonna add the offset. So if I type in 1, right, it's gonna take that 1 and it's gonna add it to 30, which makes it 31, right? We have to do the ASCII conversion this way. Then on the second input, I'm sorry, I'm skipping a line. We're gonna take that and we are going to move it to another register. The reason why I'm moving it to register 1 here, right? Because at this point, I'm at hex 30 plus whatever the value is. I'm going to move it to register 1 to free up register 0. Okay. Otherwise, you're going to have, it's going to lose the data because I have a second input. So the first input, whatever the character is, it's gonna add that to whatever I fill my label. Okay. And then I'm gonna take whatever that value is after I add at register 0, and I'm gonna move it to register 1. And how I move it to register 1 is I add 0 to it. So if I have 30, hex 30, I add it with 0, which is still hex 30, and I put it on register 1. Okay. Then for the second input, it's going to come in from register 0. Again, I'm going to take that. I'm going to add it to whatever I fill for the label. And then I put it onto register 0 again. So input 1 is at register 1. Input 2 is at register 0. Then after that, I'm going to go ahead and add them together, right? So let's say I ask the user to input number 1, like the enter a number. I put number 1, 1 plus hex 30 is hex 31, right? And then I have the user input the second number. Let's say they input number 5, right? Hex 5 plus hex 30 is 35. So it's going to take 31 plus 35, and it's going to store it into register 2. Okay, so that's basically all of these are for input and adding those numbers, those input numbers. On the next section is we're going to have to print the result. So again, we are going to load effective address, which is the address going to go into register 0. And this is the label message, MESG. And we're going to put. So load the address so we can output the string. Now what we're going to do is we are going to move, right? Remember that here is where our result is. This is register 2. We got to move it to register 0 to output, because that's the purpose of register 0 is input and output. So we're going to take the result and we gotta move it to register 0. So on this line here, when you do an add, we add it with 0 because itself, right? It's gonna be equal to itself after we add the 0, and we're gonna put it into register 0. So if I have, like, let's say hex 32 plus hex 35 in register 2, add it with 0 and put it on register 0 so I can output. Then I'm gonna load register 3 with hex 30, okay, to add. So when you coming back to here, okay, remember that for the hexadecimal is 31, and I wanted to make it 1, right? I have to subtract 30. In order to take 1 and make it into hex, I have to add 30, right? So if I add 30 at the beginning, I have to subtract 30 at the end to revert it back. So if I subtract 30 at the beginning, I have to add it back so that way it can convert it back to text. Hex represents hexadecimal. It's the type of number that we've been working on. So hexadecimal for X. X0 is just hexadecimal 0. So here is where that you would have to add the 30 to make it back into ASCII. So at the beginning, if we subtract 30 to get it from 31 to 1, right? Let's say that that's the number 1 for the input. We have to add it back so that way we can convert it back, right? So for the offset, you have to change it back because we are doing ASCII conversion. And then, so once we add the 30 to get it back into the ASCII character, we are going to display the sum. So I would take that, add it to my label, which is the offset for 30, add it to 0, and then I output. Then we're going to do a stop. Here's our data section. We have a string, the sum of the 2 input, right? And then we're going to fill FFD0. And if you don't believe me, you can take your programmer calculator and you can put in 30x, right? Or for the 30 hex, what that equivalent to. Okay, so FFD0 is going to be your negative 30 hex, where we subtract 30, and then your regular 30 hex, where we add 30. Okay. So your program should look like this. Should be 3000. I'm missing a 0 there. Okay, so we have 2 input for this one. So when you, after you assemble your program and you run, it's going to wait for your input. So file save as, and on this one, I'm going to call it L2ex4.asm. Click save. And then you just go ahead and assemble or upload and assemble on the website. And then you run on, for those of you who are using PC, go here, initialize your machine, open up your object file, and then run. So it's going to wait for your input, right? So let's say I'm going to take 1. Remember, right, hex value plus 2, right? It gives me 3. Now there's limitation in this program, right? It's only going to do 1 digit, and you are going to be limited to the cap, which is 0 through 9. So test it with the small number. Okay, copy and paste my code into the simulator, then press run. Upload the ASM file doesn't work, however. Okay, thank you. It doesn't take your ASM file. Okay. Let's see. It's the object file that you, yeah, you can assemble with that, but because you don't have an assemble with your Mac. Let's see if I can drag it. Open assembler. Okay. Paste and yeah, so you can paste your code this way. I see what you mean now. Okay, so you can do it like that. So for those of you who are using the website, right, you can do it like this. When you attempt to drag the file, what's going to happen is it's going to tell you that it wants you to upload the code. And then, so for example, if I try to do this, right, and then you're going to click open assembler, paste your code in here, click assemble, and then load to simulator, and then click run. So there we go. Okay, that was the previous one too. Questions? Okay. So as you test your program, if you test it with symbols, right, you're going to see that this program is limited. Coming back to the ASCII table, if you're looking at some of the symbol, right, if we're using symbol, there is specific value for certain symbol, and as ASCII is used, right? So if you have hex is 24, right? Is that going to be, so you're going to see that it's a different symbol that's giving you. So there is limitation in that program. We will address that down the line on how we would be able to look at ASCII conversion that's more effective with upper lowercase or certain values. Because for your project, you need to know how to write a program with input and output. Okay, any question? All right, so today, right, to really sum up, we learned how to write very basic program. I want to introduce you to outputting text, inputting characters, and converting it to ASCII. We will have many other ways to do that, and you will see it down the line. Okay, and then be able to assemble your program after you write it and be able to run it. Screenshots of code and console and simulator if possible. That's fine. And you can put it on all one document. You're welcome. Any question?
Yeah. Can you go over the difference between LD and LEA?
Yeah, so LEA, it bypasses, we will learn, I will expand on it a little bit more, but LEA is, it's gonna load, it's a pointer. it's gonna load the address of where the string is. LD is actually the initialized value with the fill. So when I do an LD like this, it's gonna load the value to that register 3. See how this line is LDR3 hex 30? So hex 30 is filled with hex 30. So it's gonna take this value and it's gonna put it into the register. Where LEA, it's only gonna put the address of MESG, which is the string, to the register.
Okay, so mostly LEA is for string
Yes,
and
that's
LD
what we
is
mostly use. LD, you
okay.
can use it with, you can load value, to it. You load a label. So normally we fill a label. So think of label as like variable, and then you declare it with the value by using fill, and then you would load the name of it to the register. Yeah, so when it does that, it's going to take the actual value and it's going to put it into the register when you do an LD. And we'll talk about LDI, which is an indirect load as well.
Thank
Yeah,
you.
you're welcome. There are quite a few loads. I think that could vary from one assembly language to another, similarly that you see across many assembly language. On Microsoft ASM and NASM, what you do is you have to tell it load to a certain bit on the word with a value. So you would do like LD or load, like the word load. Bit 2, you would say 2:3. That means that I load 3 to the second bit. And so it's a little bit more complicated. I really like teaching LC3 because it's easy for you to understand. But ultimately, to answer your question, one stores an address, the other is actually the value. But in the background, we'll talk about what is the mechanical difference between the two.
So if you do greater numbers than 5, there's not enough memory, or how does that work?
Yeah, so coming back to this, right? I'm gonna come back to the top real quick to tell you, and we'll expand on this. So your operands, they're a specific number of bits. Okay.
Mm-hmm.
And then so when it exceed the number of bits that can store the value, it basically overflows, so it couldn't give you the output.
Okay.
Yeah, because there's 16 bits word. We already used up 4 for the load, the add, or whatever. And after that, there are a certain amount of size that it used for the actual value. So when it let's say that all of those bits are 1 and you can do the binary conversion, it's only able to, when all of those bits are on, that's a maximum capacity for it.
Okay.
Yeah, so when you're handling larger number, you have to do multiple instructions and you have to do multiple adds. And
Right.
that's how the system works, is that's how it's able to store it into different memory cells.
And for the symbols, a possible result would be when you subtract the hex, or when you add the hex and subtract the hex, it will do it from the ASCII table, right?
That's correct.
So if you do those symbols, it'll just give you something else.
That's right, because it's not the scale for that program. The limitation is the scale that we're using is not fully supporting the ASCII table, right?
Yeah.
Because we're simply using a 30 offset, that's not enough. So if you have to take a look at the ASCII table and how that the scale, the difference between the table and what numerically what that converted, because we're simply only looking at like some of the beginning values, so it's very limited. We'll expand on this, and you're gonna see ASCII conversion continuously in this class until you get very comfortable with knowing what that is and using it. Okay. Good. Now you see what the computer sees though. Awesome. Other questions? Okay, so we finish up the lab for now. That is this, chapter 3 talks about gates, but when you go into the next few chapters in the book, it's gonna go more in depth in, instructions, load, add, and so on. And in my lecture for next week, I'm gonna cover and we're gonna break down some of the simple things that we're gonna be using. And as we move along, you're gonna start with this, but by the end, you're gonna write functions, you're gonna write recursive function, you're gonna write stacks, you're gonna write a lot of different things. So, you will have a full-blown program by the end of this course. I want to say by week 11 or so. So you should be able to write your own assembly program as a project. Okay. All right. I have had students that turn in a full calculator program in assembly, 1,010 lines, and I read every single line. So, but we will go through the code one line at a time, right, in the future. So if you didn't understand, go look through the code today, right? Go back and watch the video and then contact me or come to my office hours. Sometime if I don't turn on Zoom, it's because there are students physically here in my office. And sometimes they want to go over their resume or they want to talk about something more private. So I don't turn on Zoom, but I usually jump on right away. But if you need to make an appointment, let me know. I'll help you. Okay. All right. So I'm going to stop recording.